Hey guys, welcome to my YouTube channel, and this is my very first video. Today I'm gonna address the issue with the dialect interpretation of how gravitational time dilation works. Well, actually, I'm not going to make a full video because we can see 17 minutes right here. It's actually very long, and if you did not watch this video, I recommend you to watch this video first, then come back to my explanation, because I'm only address the crucial point here, that is his interpretation is wrong. Now we're going to watch. So first of all, he going to divide an interpretation for the escape velocity. The escape velocity here is 2gm divided by r, and the similarity between the Lorentz equation, square root of 1 minus v squared over c squared. This term is very familiar in special relativity because this term it only means the gamma factor. The gamma factor is this term, which is appear everywhere in special relativity. You guys probably know this. And this is Lorentz equation. This is Lorentz equation. Alright, now I'm going to show you the formula. So Dialect says is correct. That is this term is for gravitational time dilation. It kind of looks like this factor of gamma, but it's the square root of 1 minus 2gm divided by r c square. We can see that the c square in the denominator for both of this expression, which is c square appear here and c square appear here. Now we can say that this term here is actually velocity square, and velocity square equal to 2gm divided by r, which is a constant in Newtonian equation, which is say that this should be the escape velocity. It's kind of like the same like the structure radius had nothing to do with the, I mean that we must know in Minkowski geometry, the light current, etc., and we had to move to general relativity. But then it's come down that the structure radius look exactly like the escape velocity formula, which is ridiculous, right? Well, that's not a that's a fun constant between classical physics and modern physics. So we understand why this term looks exactly like the 1 over gamma, the inverse gamma formula for the very equation in special relativity. Even though we are dealing with gravitational time dilation, which only depend on altitude and the curvature of spacetime, which had nothing to do with special relativity. So that's the mystery. I'm going to help you to solve that. So first, now we understand why this term is actually in general relativity. I must this term in GR. We have this, which is okay. Oh, sorry, I pointed this out. Okay, never mind. Now watch this video. It interprets that the similarity arises because the objects must accelerate, and when it accelerates, it has to accelerate to maintain with the natural movement of the wrist, which is here called the contraction of space, a river model.
Our clocks have a velocity v with respect to this particular flow field.
Oh yeah, so this flow field, a flow field is called his river analogy, the river model. So the clock had to accelerate in order to standing still the gravitational field to maintain a constant radial coordinates. Just like here, we standing on the planet, we have to accelerate to be standing still on the surface of the planet. So space constantly flow into the center of the planet. So this is the very good analogy. Actually, it's not space that flow though. Science Click English, a very good channel that called Science Click English help on now. It's just syncing the volume between geodesic, because if space actually flow, and if we have the clock here and flow, it had a final velocity here, then the clock drop here should travel that same velocity, but it's not, because it's not actually space that's flowing. But the issue is this:
velocity which they maintain via their constant outward acceleration with respect to the mass.
So here say that the clock had to accelerate is the change in velocity. It had to accelerate to standing still. But what is this v? This velocity v right here is actually the capture velocity. He changed the meaning from the escape velocity. Here's the escape velocity in the Newtonian mechanics. He just changed the meaning into the capture velocity. So no longer escape velocity. It means the velocity it had traveled with respect to the flow of space, a local flow right next to it. It means that according to this space it at rest, the object had to travel at this velocity v, to standing still here. The flow had different speed according to the region, but the speed of the flow is actually local here. We have to travel at the speed v in order to maintain a constant position altitude. Now I'm going to show you how is this wrong. A commenter on his video has helped me to know the truth. I didn't realize this before, because I realized maybe there's a paradox with this analogy, but now I understand. Suppose we have a planet with the mass m, which is very big. Let's say me standing here as a distant observer. Let's call me an A observer, and I see my friend let's actually falling into this mass. So this is LS. So suppose in the Newtonian mechanics here, that attracted to this mass m, because here is nearing it and here accelerating due to gravity. In general relativity, it's only mean that you follow a geodesic, not because it's influenced by a force. But let's say that in this picture look Newtonian for example, for things to make it easier. Now in general relativity, we had time on our clock, and time on the clock we know it must flow slower because the time dilation depends on the altitude r, and we know that the clock of the freefall observer must be slower. But at Dialect say that space is flowing inward, and the velocity v here is moving equivalent to this velocity. It actually the capture velocity, that if this guy want to stand in a constant altitude, he must always accelerate to have the speed with respect to the flow opposite direction. The flow moved in the opposite direction. You have to move forward to maintain the constant distance. So if Alex is falling like this, then according to the fluid analogy, the river model, he should be standing still with respect to the flow. This means, according to the Lorentz equation, this must be 0. So we have 0 square over c square, which will turn out equal to 1. So there's no time dilation. If we want to interpret this literally at a time dilation, then it's not gonna happen. Time dilation will disappear completely when the object is in free fall, because according to the space locally, space that flow into the mass, it is not moving at all. Yet this is the paradox. In reality, the math of general relativity say that it's also happen. It's always happen. Now we can finally move to my analogy. This is something that I discovered many years ago. Now I understand what it means. So let's say that. So before I come to the derivation. I want to show you a simple experiment in physics. Suppose a person here want to drop a steel ball from the mountain Everest to the sea level. I said the sea level is here. What is the final velocity an object will have when it almost hit the sea level, ignoring air resistance? Well, in Newtonian mechanics, we just need two simple formula. We need to figure out the time required for falling. In this case, we can use this formula because we can assume the distance here is, let's call this h, to be okay. So the gravitational acceleration here can be constant. It's not actually constant though, but let's assume it is because distance on the mountain Everest is only about nearly 10,000 kilometers. So this is very easy to see that gravitational acceleration do not vary much. We can assume this constant. And from this t, we can compute the velocity because we know velocity equal to acceleration multiplied by time. Therefore, it's equal to this formula. It's the final velocity of an object. This is the final velocity. Okay, so let's compute this. Let's try to compute this first. So let me compute this. Let me make some everything new here. Let's compute the final velocity by taking the square root of 2 multiplied by 8,848 meters divided by gravitational acceleration. We figure out the time, about 42 seconds. And we multiply by the acceleration due to gravity. We figure out the final velocity must be this, 460 feet. Now I want to imagine at the point he dropped his ball, let's make a gravitational time dilation factor, which is equal to, sorry, let's make an inverse, just equal to t prime divided by t. And at this point, local point right here, let's say the value is just equal to 1. The point here is the point where we drop the ball to the ground. When the ball is released, it's in free fall. At this point, gravitational time dilation between two infinitesimal points here, it will be equal to 1, because we are comparing time flow right here to time flow right here. But what about this region here? Let's say about this region, what is the value of gamma? Well, to calculate this, we need the gravitational time dilation formula, which is this: t prime over t, which is equal to, we need two expression of with what we saw earlier. Is this the escape velocity here? This term RC square in the stoichiometric here. And we need to change a little. We want to be the value to be low. Let's assume this is R naught c square. R naught simply means the radius of the Earth, and we have to divide this by this term again. The key is that this term appears twice, and I will get to that point later. Divided by, now we have the RC square, where R is actually R naught plus the altitude A, which is A equal to the number we saw earlier. So with this formula, we can calculate the inverse gamma factor of gravitational. Now I will let you take a look to wrap this. So we saw the formula, we saw the final velocity earlier. Now let me compute the gravitational time dilation. Like the gravitational constant, the mass of the Earth, and we have to remember that, okay, so the radius of the planet multiplied by the speed of light square and divide by this term again. Oh, sorry. And in this term, we have to add the radius of the planet with the height of the mountain Everest. So this is the amount of time dilation we calculated earlier. Now let's see the magic how it happened. Now, this analogy again, we come back to special relativity, the very familiar time dilation formula. T prime equal to T multiplied by the square root of 1 minus V square over C square. This is special relativity. However, let's rewrite for velocity V, which is equal to C multiplied by the square root of 1 minus T prime divided by T all square. Yes, this formula can compute the final velocity just like I do earlier with the Newtonian formula. So right now I have this value here, which is no longer a number of 1, but will be lower than 1, which is equal to 0. Let's say 99999. The only thing that we need to only know that's the value here is smaller than 1, and this value is equal to 1 at the point the object will drop, and this value is less than 1 at the object where I have the final velocity here. So let me calculate. Now, as using this formula, speed of light multiplied by square root, which is our good old Lorentz time dilation formula, and boom! What? Did you see that? So what's going on? We come back to this analogy where the I lost this. Sorry. Let's come back to the planet. And we have earlier the person standing, a distant observer standing here. We have a radian of time. Time flow faster here, and faster here, and slow down here, slow down here, slow down here. Alright, so a person who is in free fall will have the time dilation be equal to 1 at respect to his movement, and at this point it's lower than 1. The final velocity will match up the kinematic time dilation in special relativity. So this is completely opposite to the analogy of dialect, which is say that the river model, this person should not experience any time dilation. Yes, he did, and it must match the amount of gamma factor here, which is less than 1 in the formula C equal to V multiplied by the square root of 1 minus T prime over T square. Now we can talk about the mystery of this expression right now. The expression that's equal to 1 minus 2gm over RC square in the stroke geometric, where V represent his. Sorry, people are too loud in this room. Okay. This velocity here, dialect chain, this formula form dialect chain from escape velocity. The meaning of this formula from being escape velocity to capture velocity. But this is wrong. Actually, it must change from escape velocity to final velocity. How is it possible? Let's solve Newtonian differential equation for acceleration. So we have the expression here that equal to negative gm divided by r squared. We can compute a simple integral. The integral of v dv, which is equal to the integral of this term dr. So we in final we have this 1/2 dr divided by dt square equal to gm over r plus a constant, let's call k. Now we can interpret the constant into the value of r0. Remember what I said earlier? I said that you always need two terms in gravitational time dilation, which is r0 and r. We need two terms here, always, because we compare the time dilation between 2 points. And as turned out in our differential equation, it will look like this. So this is just velocity square. Its mean velocity must be equal to this. The full expression will look like this. dr divided by dt must equal to square root of 2gm divided by r0 minus 2gm divided by r. So this is no longer the formula for escape velocity anymore. This is the formula for final velocity when we compute the point here and the point here. Let's say that if it's math, our calculation. Oh, I'm sorry, people were too loud. Now we need, let's test our formula. So we have the square root of 2gm over r0 minus 2gm over r. Let's compute 2gm over r0 first. 2gm over r0 and 2gm over r. Okay. Then we take square root of this minus for this. Oh, it's matched the number earlier. So yeah, this is the formula for final velocity of an object. Well, let's say the mountain Everest here again. The sea level here. We see that we can say this at r0, which is the radius of the planet, and this is r, the distance r0 plus the age, the height of the mountain. So yes, this is true because the expression here is not the escape velocity anymore. It's not the escape velocity anymore. It has changed the meaning, but it changed to the final velocity, which is this expression. Here we can compute by dividing a differential equation of gravitational acceleration, which is this equation. Not because it is the capture velocity in order to standing still relative to the contracting risk at dialect point out. Because we can see that another problem with this analogy, we have the mass m here. If space flow like this, space constantly flowing to the center, we will have a problem. The problem is that if we have an object at right here and flowing relative to space, it will have a final velocity very raw. Let's see, it flow to here to here. Then we at the same time we drop another object. because the width contract at the same rate, we should expect the width to include both objects, causing them to have the exact same final velocity. But yeah, it did not happen. It's completely relative. So this analogy is actually nonsense. Actually, it is the contraction of the geodesic. Now we understand why the formula looks very much like escape velocity, because it comes from this formula. It comes from this formula here, which is the formula for final velocity. This term is actually equal to v, and that is why, my friend, this is why the term here and the term here are similar. I hope you like the video. Thanks for watching, and if you like video like this, please leave me a subscribe. My name is West Mindang, and I will continue to do video in future.